this class we will learn the design of some of the common digital elements. Mainly these elements are frequently used or very popularly used for the all the other digital designs or the some bigger circuits. Now, before we start the design of these elements, first we see the last is quiz question. So, the question was the design it is a design of a 4-bit parallel adder using full adder as its components, and then from form an 8-bit adder from this 4-bit adder. Now, already we have read the full adder module. It is that sum was some form AX or BX or C, sum was AX or BX or C, or the AB are operands and C is the carry in, and this is the current carry which is AB plus BC plus CA. Now, this is one module already we discussed. What we can see as if this is say one module, we are thinking as if this is one module whose, so this is a black box, there are two inputs AB, another input C, that means there are 3 inputs and 2 outputs S and C. So, what we can see as if the whole circuitry is in between this A, B, C, S and carry, sum and carry, and this we are calling a full adder FA. This is my full adder module. Now, this is a 4-bit full adder, that means I have to add A3, say A is a 4-bit, A3, A2, A1, A0 and B as B3, B2, B1, B0. This we will add. So, initially the carry, the initial carry we are considering as if C in, and these are carries are for here the carries are C1, here the carries C2, this is C3 and C4. This is the notations of the addition modulo or this 4-bit adder. Now, that just now we have drawn a full adder module, we have taken 4 such full adder module. What we have seen that one full adder module there are 3 inputs and 2 outputs. See, these are the 3 inputs, 2 operands A0 B0, that means now this from A, so A, that A3, A2, A1, A0, as if this A0 is coming here, and B, B3, B2, B1, B0, this B, this. So, A0, B0, these two are fed to the first full adder module, and this is the carry in, the initial carry. So, these are the 3 inputs. The 2 outputs are, this is the first bit sum, that means the 0th bit sum of 0th bit S0, and the carry of the first bit, that means carry of the sum of the first bits C1. Now, it is fed to the second full adder module, where the operands are the A1 B1, means the second bit of the two operands. Again, see here, for the second full adder module also there are 3 inputs A1, B1 and the C1 means the previous carry, and it generates 2 output C2 and S1. So, S1 is the second sum or the second bit sum, and C2 is the second carry bit. Similarly, it is fed to the third full adder module, and A2 B2 is the input, S2 and C3 are the outputs, and for the fourth the A3 B3 are the of two operands and S3, and the final carry we are calling that this is C0, or that this is my final carry CO. So, now this is my 4-bit parallel adder. We can tell that this is the 4-bit parallel adder which was drawn from taking the full adder as the module. Where FA is the full adder module. Now, the second part was that taking, now I will treat this as a module. So, this is a 4-bit adder, and from there some 8-bit adder we have to draw. Now, we see. So, that means here now this 4-bit I am writing 4FA, means this is a 4-bit full adder, another 4FA we have taken, because for 8-bit we need. Now, there are 4 inputs for the 4-bit, actually there are 4 A's and 4 B's. Similarly, see for 8-bit adder, that the inputs are, so these are my A0, A1, A2, A3, then A4, A5, A6, A7, and these are the B inputs B0, B1, B2, B3, and these are B4, B5, B6, B7. So, 0 to 7 these are the inputs. Again this is my carry in, and these are my sum bits S0, S1 to S7. And similarly here, now these are, here there will be 4 sum, here there will be 4, because we have taken the 4-bit adder. So, there will be for A0 B0 summing, it will generate S0. For A1 B1 it is S1, A2 B2 it will be S2, A3 B3 it will be S3. Similarly, for A4 B4 it will be S4, S5, S6 and S7, and this is my carry out. So, in the previous case we have taken the full adder as the module, and then we have designed, or we framed a 4-bit adder, and now taking two 4-bit adder we have done one 8-bit adder, and now here that 4-bit full adder as if these are the module or these are the elements. Now, this just now what we discussed, that as if full adder is the module taken for designing a bigger circuit, or when we are designing a 8-bit adder, we are taking the 4-bit adder as the module for designing the circuits. So, in this way we can take one smaller, or from some smaller gates first we design another bigger module that can be the component of another bigger circuit. So, in digital design there are some traditional elements, and normally for bigger circuits or all real life circuits these elements are being used. These are some specific functionalities and these are being used. So, this class we read some of these type of elements. These we are calling that the common digital elements. So, first one we will read is the line decoder. So, first we define what do we mean by a line decoder. So, line decoder, or simply we can tell decoder, is a circuit that allow us to activate an output line by specifying a control word. It is either active high or active low, means the output can be active high or active low. Active high means it sets a particular output to logic 1, while the remaining outputs are in logic 0. For a 2/4 decoder, 2/4 means, so this is a line decoder. So, what we can do, see the for a line decoder, if we draw that, see there are just block diagram level, if we draw that thing, then there will be two control lines. We are telling these are S1 and S0, and output, there are 4 output lines. These are D0, D1, D2, D3. Now, these are called the S0, S1 we are calling select lines. So, by applying a particular pattern in the S1, S0 lines, we are calling the control words to the select lines, what we can do, that one particular output lines can be made high or low. So, this is the function of the decoder. So, this is my 2 to 4 decoder. Now, if we write the operation, see we have again if I draw that, this is my decoder, the two select lines S1 and S0, and this is my D0, D1, D2, D3. See here these are the control bits. So, these are my select lines, these are my output. Now, if we put 0 0 in the select lines, then D0 will be active high. If it is 0 1, then D1 will be active high. If it is 1 0, that means S1 is 1, S0 is 0, then D2 will active high, that means logic 1 active high means this will be logic 1, and if S1 S0 is 1 1, then D3 will be active high. So, this is the operation, or what we can tell that again the input output relationship, because my select line is nothing but the input output relationship of this particular element. So, now we have to draw the circuit. So, in the same way here there are actually as if 4 outputs and this is the 2 inputs. So, for 2 inputs I can draw the map and I can, because this is very trivial situation, and from there I can make the expression. But here it is very simple, because if it is 0 0, this is 1. So, how we can write that thing? This is 0 0, this can be a see that S1 is 0, S2 is 0, then it is giving my D0 equal to 1. So, I can write D0 equal to S1 we have given S1 S0 S1. So, this is S0, I can put D0 is S1 bar dot S0 bar. So, this is the when S1 equal to 0, S0 equal to 1. Case 2 is S1 is 0 and S0 is 1. This puts that D1 equal to 1. So, that means D1 is S1 bar dot S0, and in the similar way I can tell that D2 is S1 dot S0 bar and D3 is S1 S0. Now, one thing is that when one particular output line, that means any one of the D0, D1, D2, D3 will be active high, then the remaining 3 must be active low, means that it will be logic 0. Now, see when this is when 0 0, when D0 is selected, that means D0 is 1, then what is the status of D1, D2 and D3, because they must be 0. See that S1 is S0 is 0, S1 is 0 bar, so this is 1.0, means this is 0, logic 0. Similarly, this is S1 is 0 and this is 0 bar, so this is 0 and this is 0 0, so this will be 0, so it is valid. And for the other cases also, that means when the select line will be 1 0, here S1 equal to 0 0, when it is D1 will be high, so D1 will be high when S1 0 S0 1, that time that other D0, D2, D3 they will be logic low or logic 0. Similar thing will happen for D2, D3 also. So, the internal circuitry mainly does this thing, that this S0 bar, S1 bar, S1 bar is 0. Now, see that the control circuit is like that. See here, D0 will be active high or D0 equal to 1 when S1 bar is 0 bar. So, this see here S1 is fed to one inverter, that means this is my S1 bar, this is my S1 bar, this and S0 inverted. So, this is my S0 bar, S1 bar, then D0 will be 1. Similarly, D1, this will be S1 bar, S0. For D2, this is S0 bar, because the input is taken from the inverter output, NOT gate, output of the NOT gate. So, this is S0 bar and this is simple S1, whereas for D3 this is as it is S1, S0 and S1. So, this is my decoder design, a 2 to 4 decoder. Now, similarly, what we can do for that 3 to 8 decoder, 3 by 8 decoder, we can, then that time it will be a 3-bit control line or 3-bit select line and that 8-bit output line, that means it directs the path to any one of the 8-bit. So, no output. Normally, this is a n to 2 to the power n decoder we can design and the circuit will be similar. Now, if it is active low means for the same select line or the same control bits on the select lines, the one particular output line will be active low and remaining will be 0. That means, when S1 S0 is 0 0, that only D0 will be 0 and all D3, D2, D1 will be 1. Similarly, when S1 S0 is 0 1, only D1 will be 0, remaining 3 outputs are 0. When it is 1 0, D2 will be 0, when 1 1, then D3 will be 0, and the same thing applies. Then what will be the circuit? See, now the circuit is, see if we can draw, that means now what about the D0 functions? So, D0 functions will be S1 bar dot S0 bar overall complemented, because earlier it was active high, now it is simply that active low means 1 bar, and for the active high decoder, the last case when we have considered, for the D0 the select line was S1 bar S0 bar. So, it is complement of S1 bar dot S0 bar, which is nothing but S1 plus S0, that means the OR. Similarly, the D1 will be the S1 bar S0 that bar, that means S1 plus S0 bar. D2 will be S1 dot S0 bar, complement of that means, and D3 will be S1 dot S0 bar means S1 plus S0. Now, we can see that, or we can notice that thing, that mainly the for active high the select line or the output expression, when the select lines as of the inputs are changed, for the active high it was and for the active low it becomes the OR. Another thing, for D0 the input variables were complemented, where here the input variables are become uncomplemented, and the totally reversing we are getting, because for the active high decoder the input variables were uncomplemented and ANDed, whereas for the active low decoder the input lines are complemented and the AND becomes OR. So, this is the situation. Now, we see that how we are. Now, as it is when it is designed actually as if that same select line is given. See, for this thing that S1 bar S0 bar. So, here we have given S0 bar S1 bar, and simply that from either case that as if D0 is complemented, because it was active low means that for the active high case it was 1 was generated, as if this 1 becomes 0. So, it is complemented. So, the circuit remains as it is, only the AND becomes the NAND, that means every AND now changed is a AND followed by a inverter, which is nothing but a NAND circuit, as if only the last output line has been complemented. So, this is the simple modification, or with the simple change, that active high 224 active high decoder can be changed to active low decoder. Now, the second element we see, the digital element, which is a multiplexer. First, we define a multiplexer. Normally in short form it is called a MUX, is a logic component that has several inputs but only one output. MUX directs one of the input to its output line by using a control bit word to its select lines. So, if I draw a block diagram, see, say I am taking a 4 to 1 multiplexer, that means there are 4 input lines. is a 4 to 1 marks, and there are select line like the decoders. So, these are 2 select lines, and there is only one output line. Now, the function is that if we apply a particular control word to the select lines S1 is 0, then the one particular input will be directed to the output. So, when we change the control word to the select line, the directed inputs to the output will also be changed. So, this is the function of the multiplexer. See, if we take the S0 S1 S0 equal to 0 0, then we are selecting the P0 lines, where the P0, P1, P2, P3 we have taken as the input lines. Then P0 is directed to output. That means, whatever value I will put as the P0 input line, that will be that I will get to my output F. Similarly, if it is, it can be 0 1 1 0 or 1 1. So, if S1 S0 is 1 1, then whatever input is applied to P3, that will be directed to the output F. So, this is the function of multiplexer. Now, if we do this operation, if we explain, then again this is my select lines or control bits, this is my output. Now, what is the input output relationship? So, when S1 S0 is 0 0, output is nothing but P0, 0 1 output is P1, 1 0 output is P2, 1 1 output is P3. So, now if we write, see that I am writing the expression for the output F. So, F I can write that S1 bar S0 bar, the 0 bar this is 1, that time P0 will be my output. So, S1 bar dot S0 bar dot P0 plus S1 bar S0 for the second case, means P1 when dot P1, S1 S0 bar dot P2, S1 S0 dot P3. See, for the decoder, that 4 select lines or the 4 control words applied to the select lines that are same, only that on each cases which input line is directed to the output, that has been ANDed with the each min term. So, we got this expression for the output. So, the circuit will be that simple realization of the AND OR, and as there are some complemented input variables, so some inverter is applied to the input. Now, this is the similar circuit for the decoder. Here that for the first AND gate, this output or input should be S0 see that here the input of the AND gate, this is S0 bar, this is S1 bar, and this is my P1. P0. So, this is for actually that first input line is directed to the output. Similarly, that for other 3 inputs or the other 3 AND gates, it will happen. So, this is a simple circuit which consists of the AND gates, OR gates and some inverter. Now, this 4-to-1 multiplexer, we can treat this as a module, and for my larger design or bigger circuitry design, I can use this multiplexer as a smaller module, as if this is a basic building block of my design. And this is very standard. So, the IEEE symbol for a 4x1 multiplexer is like this thing. So, this is one box where as if there are 6 inputs, the 4 are the basic inputs and these are the select lines. Again, select lines also I am applying my control signals. So, they are treated as a input and one output line. So, this is as if this is one module, this is one 4-to-1 mux module. So, for larger circuit design, I can take this as the digital element. That is why we are calling this is also digital element. Now, we consider an 8-to-1 multiplexer, and we notice that how this 4-to-1 multiplexer can be used to design a 8-to-1 multiplexer. So, for to design a 8-to-1 multiplexer, we need the 2 4-to-1 multiplexer. See the 2 4-to-1 multiplexer and 1 2-to-1 multiplexer. First, we say as if, because it is a 8-to-1 multiplexer, how do I know, how do I select that how many multiplexer module will be needed. See here 8-to-1 multiplexer means there are 8 input lines, and for 4-to-1 multiplexer there are 4 input lines. So, at least 2 multiplexer I need to apply my inputs. So, I have got that 2 4-to-1 multiplexer. Now, for each multiplexer there is one output line. So, for 2 I have identified them as if x1 and x2 are the 2 output lines of the 2 multiplexers. Then I can define them. Already I know that expression for 4-to-1 multiplexer, and what was that? That if it is a, say if it is a number 1, this is a 1 mux 1, this is my mux 1. So, again P0, P1, P2, P3 and output is x1. Similarly, here it is mux 2, P0, P1 and this is x2. So, I can write x1 is S1 bar S0, this is my S1 S0 bar P0, S1 bar S0 P1, S1 S0 bar P2, S1 S0 P3. Similarly, for the second mux also the expression will be same, only output line is x2. So, x2 is S1 bar S0 bar P0, S1 bar S0 P1, S1 S0 bar P2, S1 S0 P3. Now that the final output of the 8 to 1 multiplexer will be that f equal to, say I am taking another select line S2 bar x1 plus S2 x2, that means another 2 to 1 multiplexer. This is a mux where only 2 input lines will be one select line and one output. This I am calling F, and the 2 inputs are x1 x2. Select line is S2. Then this is my expression. So if I redraw that thing, what will happen? That I need 4 to 1. So these are S1, S0 and P0, P1, P2, P3. This is my X1. Similarly, I need another 4 to 1, same P0, P1, P2, P3. These are all inputs, S1, S0. Now, as if another 2 to 1, and this is F, and this is a separate select lines. So, these F will be the overall, that means see there are 8 inputs, 3 select lines, so this is, these are my inputs, these are my select lines, this is my output. So this is a 8 to 1 mux, where 3 select lines are needed. Normally that in general, if it is a n bit select lines, then input should be 2 to the power n. That means 2 to the power n is to 1 mux. For 2 to the power n is to 1 mux, n select lines will be needed. Now this is the just now what we have drawn, that if from that IEEE convention, if we maintain that this is the conventional mux module, that 4 to 1 mux module, where that S0 S1 are 2 select lines, P0, P1, P2, P3 are 4 input lines for the first mux. This is my mux 1, this is my mux 2, and this is my mux 3. That output of the 4 to 2, 4 to 1 mux, these are the inputs, and another select lines are there, and this will be my output F2. Now, this is a internal logic for 1 to 4 demultiplexer. Now, multiplexer is, there are several input lines, but only one output line. Now, here the totally reverse thing is there. So, if we define the operation, here the select lines will be, if for the n select lines only one input line will be there and there will be several output line, and for application of a specific control bit word to the select line will direct the input to a particular output. So, this is the reverse operation of the multiplexer, and that is why it is called a demultiplexer. So, if we see that, that means for multiplexer, there are, say if we consider again that 4 to 1 marks. So, this is a 4 to 1 marks. To 1 marks, 4 input lines will be there, 1 output line. So, these are my multiple inputs, single output, select line will be n. Now, if it is a demarks, see it will be totally reverse thing, as if I am applying the input here. So, one single input, select line will be as it is, and the output, several output will be there. So, these are my outputs. That means, in this case the only one single input, and depending on the value or the control bit at the select signals or the select lines, that the particular input will be directed to different type of or different output lines, depending on the select lines. Now, if we see the internal circuitry, see always that one input is there, that is my x input. Now, this x is fed to as the input of all the AND gate, and the output of the AND gates are P0, P1, P2, P3. Now, depending on the other inputs of the AND gate, whether the P0 will get, that means here P0 will be x or not, that will be there. Here P1 equal to x, here P2 equal to x, here P3 equal to x. Now, one small circuit we see, one small AND gate, we take one small AND gate. See here I am giving a x, and here I want my f should be x. When I will be getting that thing? When these input, say this is my control input C. When that C equal to 1, that time I will be getting f equal to x. Why? Because if I remember that the truth table for the AND gate, then 0 0, if are the two inputs, this is my output, then this is 0 0 1 0 1 0 0 1 1 1. Now, see when that my, if these two inputs, think that as if this is my this is my x and this is my c. Now, when c is 1 means c is 1, this is the c is 1, c is 1. See what value I am giving x, here x equal to 0, that I am getting as output. That means here x equal to 0, this situation x equal to 0, I am also getting f equal to 0. This situation when c equal to 1, I am giving x equal to 1, here also I am getting f equal to 1. So, what I can from here, what I can infer that if one of the, for a 2 input AND gate, if one of the input is 1, that means in this case if c equal to 1, then whatever value I will give to x, I will get the output as it is. That means my f equal to x. So, this is my, this is called the gated output. That means I am controlling whether which one I will pass. When c, whatever c value, c is 1, whatever value I will be giving to x, that will pass. See here in my demultiplexer, actually I want that thing. Whatever value I want to give here x, that x I want that to be passed as P3 or P2 or P1 or P0. So, that means when P0 equal to x, my here there is, instead of that example I have given, that gated AND c and x, that only one input, here it is 2 input, but the 2 input should be 1. So, that means together the combination of these S0 S1 together it will be 1. So, if it is S0 bar S1 bar, and when S0 S1 equal to 0, that means for the first P0 case, that when S0 S1 S0 is 0 0, then S1 bar S0 bar is 1 and I will get P0 equal to x. Now, here the inputs are, in this case the inputs are S0 S1 bar, S0 S1 bar. So, if I put S1 S0, if for this I put S1 S0 as 0 1, then it will be P1 will equal to x, because these are 1. Similarly, here it will be S1 S0 equal to 1 0, and here S1 S0 equal to 1 1, then this is P2 equal to x, here P3 equal to x. That means, if we summarize, that if I have 2 select lines, so the 2 select lines and 4 output lines, then S1 S0 equal to 0 0 will make P0 equal to x, S1 S0 equal to 0 1 will make P1 equal to x, S1 S0 equal to 1 0 will make P2 equal to x, S1 S0 equal to 1 1 will make P3 equal to x. And that time, that to make S1, I am putting S1 S0 0 0, but I want the AND gate, these are the two inputs, say this is my x, I want my x to be, I want my x to be gated. Okay. So, I want this thing. So, together this should be 1. So, here it will be, as it is 0 0, that means it should be 1 because it is a AND gate. So, this should be 1, this should be 1. So, if it is 0, that means my S1 is 0, if it is 0 0, then 0 bar 1, 0 bar 1. So, it will be 1, and then as it is the one input is, as it these two together, S1 S0 together will be treated as one input of the AND gate, that is 1, and so whatever value I will give to x, that will be as it is passed to the output f. And similar thing will happen for other the 3 other situations, that for the P1, again this is my x, f means my P1, and here again I want the 2 input together as 1. So, is I have given the situation select control bits to the select lines as 0 1. So, S1 bar, so this is my S1 bar, this is my S0, because here S1 is 0, S1 is 0 is 0 1. Then the text will be passed as similarly passed to P2 or P3, and in this way we can design the circuits. So, I want to end this class here. Thank you.